So once again, up to this point, we've add matrices together, we subtract matrices, we did additive inverses, we set matrices equal to one another to solve for variables. But again, we're focusing on one topic today, and that's multiplying them. Okay, and it can be done. The matrix that results when we take two matrices and multiply them together. Back in the day when we took 3 times 4 to come up with 12, what did we call this 12? Product. Therefore, when we multiply matrices together, the result is called the product matrix. And that's what we'll be looking for today. Now understand, not all matrices can be multiplied together. There's a system in place that allows us to do so. First thing we have to do is be able to identify the dimensions of a matrix. Okay? So suppose we have matrix A and matrix B and we want to multiply them together. Let's just ignore these. Let's go, I can't go that far. Let's pretend that matrix A is a 3 by 2. Matrix B just happens to be a 2 by 2. So the question is can we find the product matrix? Is it possible to multiply those together? And where we look at is the inner dimensions of the two. If they match up, yes, they can be multiplied together. So if we look at the first example, 2 is equal to 2, yes, we can multiply. If we look at the next example, say matrix A is a 2 by 4, matrix B is a 2 by 4. Okay, we look at the inner dimensions again. Is 4 the same as 2? No. So we cannot multiply those two together. Yes?
Does the order of them matter? Like, could you have matrix B, then matrix A?
Yes. So the point, and I was going to say that for the end, but you brought it up now, and that's fine. A times B is not the same as B times A. And that's one of the rules that we break from our old school math. You know, 3 times 4 was always the same as 4 times 3. Well, that's no longer the same when we multiply matrices. So the order in which we multiply them is vital. That's good that you bring that up. So let's go ahead and go through a couple of examples and you'll pick up on it. You know, we want to determine if the product of the matrices is defined, which means does it exist? Can we multiply these two matrices together? And if so, we're going to give the dimensions of the product matrix. So we begin with matrix A, and we are given matrix B. We know that matrix A is a 4 by 3, and we know that matrix B is a 3 by 2. So A times B. And we ask ourselves, are the inner dimensions the same? Are they in this case? Yes, they are. Those two are the same. So yes. Now the cool thing about it is we know if it can be done just by looking at the dimensions what the size of our product matrix is going to be. You know, when we multiply these two matrices together, what is its size going to be? And we can do that by looking at the outer dimensions. We know that it's going to be a 4 by 2. So we know that A times B is going to result in a 4 by 2. Let me ask you this question. If I wanted to take B times A, is that possible? Well, let's write it out. B dimensions are 3 by 2. So B times A, is it possible? B is 3 by 2 times A, which is 4 by 3. Could we do that? No, because if we look at the inner dimensions, they are not the same, so no. That product matrix does not exist. So we proved our point. Does the order matter? Yeah, obviously it does. A by B exists, but B times A does not. Okay, let's go to another one. If we want to find AB, A is a 3 by 1. We want to multiply it by this 2 by 1. Where do we look again? Well, we look at the inner dimensions. Are those two the same? No. Seems kind of goofy or almost foreign, like really? That's where we look to see if we can multiply these two together? Yeah. So here we go. They want us to find AB, which simply means to multiply matrix A times matrix B. Now if we look at the dimensions of A, we recognize that it has 3 rows and 2 columns. If we identify the size of B, we have 2 rows and 2 columns. Do the inner dimensions match up? Yes, they do. So we can find AB. The other thing we know without doing any work is the fact that what's the size of AB going to be? It's going to be a 3 by 2. So here's what we want to do. Let's go ahead and I'm going to copy these down. 2, 3, 4, -3, 1, and 5 times 1, 4, 2, -5. And we said it was going to be a 3 by 2, right? So let's set up that 3 by 2. Let's create 3 rows and 2 columns. Make sure you give yourself plenty of space when you do this, because there's going to be a little bit of arithmetic involved here. Now the other thing I've told my students to do in the past, and I'm going to tell you guys to do as well, is let's label each row and each column. This is going to be column 1, this is going to be column 2. This is row 1, row 2, row 3. And here's the game. Start by picking an element you want to solve for. So let's begin up here in the top left-hand corner. If I want to find that element, I need to use a row and I need to use a column. And it always goes rows, then columns, right? Just like when we identify the size of it, RC. We are going to use the row of the first matrix times the column of the second matrix. So, the question is, which row and which column do I use? Well, notice that this element is located in row 1, column 1. So what I want to use is the row of the first times the first column of the second. And what we want to do is multiply left to right, up to down. So, 2 times 1 is 2. -3 times 4 is -12. We add those together and we have our element. Let's try another one. I want to find that element right there. Which row and which column do I use? Well, I use the first row, second column. So first row, now I want to use the second column there. So 2 times 2 is 4. -3 times -5 is 15. Starting to see it? Okay, let's do another one. What row and what column do I use here? Sydney, you said it? Row 2, column 1. So row 2, column 1. 3 times 1 is 3. 1 times 4 is 4. Let's find this one. Row 2, column 2 is where that one is located. So row 2, column 2. 3 times 2 is 6. 1 times -5 is -5. You always work from left to right, up to down when you multiply those together. That one. Row 3, column 1, right? Row 3, column 1. 4 times 1 is 4. 5 times 4 is 20. Last one, row 3, column 2. These will always be plus signs in between those products. Let's add them together and we're done. 2 and negative 12 is negative 10. Negative 25 and 8 will get us negative 17. There it is. So obviously there was a reason why I made today a one lesson day. Okay, we're gonna get a lot more practice with it. Before we get there, let's talk about a few terms that may pop up. A matrix with the same number of rows as columns, like a 2x2 or 3x3, notice that creates a square, hence we call it the square matrix. The diagonal from the upper left-hand corner to the bottom right-hand corner of a square matrix. So the main diagonal would be the 1 and the 7. Okay? Main diagonal. I'm not overly concerned with that term, so if that's a little confusing to you, don't worry about it. A square matrix with 1 in every entry of the main diagonal and a 0 in every other one. That is called the identity matrix. If we have a 3x3, that is the identity matrix. What does that mean? Let's just go back to our old-fashioned numbers. If I have 3, what number did I take it by to come up with 3? 1. If I have negative 7, what did I multiply it to come up with negative 7? 1. This was called the multiplicative identity, correct? This thing is playing the role of 1 when you multiply matrices. So, simple enough. If I give you this, and I want you to multiply it by this, what is that going to equal? This thing, right? Because what did we do? We took it times 1, essentially. Believe it or not, students will forget this is the identity matrix. And I believe it's on like test 5 or 6. They will actually do the entire process and realize that they have come up with the exact same one. So I appreciate your 15, maybe 20 minutes of work that you maybe didn't have to do. Okay, so if you recognize that, make sure you do that. You know, if we take a look at example 3 on page 56, at the very bottom page, they took matrix A times that identity matrix 3x3, and they actually did the work. But notice the very last line, what did they come up with? It's the same thing. It's matrix A. So we're not going to do one of those. They did the work for us. It's the same thing. It's playing the role of 1. So just make sure you're leery of it. As soon as you see this guy, ooh, life became so much easier. Okay? What if I flip the two of them? Does it still work? Yeah. Because again, same concept. You could have taken 1 times 3 and still got 3. Okay, that holds true. Okay, last one. then I'll let you practice with this. So we have 3 people. They're getting ready to go camping. Here's their camping gear. Here's the cost for the gear. And actually what we can do is we can use matrix multiplication to figure out how much each person spent altogether. Let's start with this first matrix. We did this the other day. Just take the table and turn it into a matrix. And what we are going to do is we're going to times it by the second one. Let's identify our dimensions here to make sure we can do this. This is obviously a 3 by 3. What's this one? 3 by 1. Do the inner dimensions that equal one another? Yes. So what's our product matrix going to be? 3 by 1. Good. So 3 rows and only 1 column. Okay. Now before I told you, identify the columns, identify the rows. At least to begin with, I want you to put the R1, R2, R3, and C1. Once you get more comfortable with it, then you may not have to do it. But let's start with this one. If I want to find that element, what row and what column do I use? Well, row 1, column 1. Row of the first times column of the second. It's always horizontal and always vertical. 1 times 16 is 16. And then continue to work from left to right, up to down. 1 times 50. And 3 times 85. 255. Let's move on to the next one. Now we are using a row 2. 1 times 16, 1 times 50, 2 times 85. Lastly, that is located in row 3, column 1. Row 3, column 1. 2 times 16 now is 32. Be careful here. A lot of people will put 50. What should I write? 0. 0 times 50 is 0. 1 times 85 is 85. (32 and 85 ends in a 7. 117. So what do these numbers represent? Well, the cool thing about matrices is they hold their structure, or the organization of it. Notice when we set up our first matrix, it was John, Maylin, and then Rochelle. So the 321, that obviously goes with John. 236 is how much Maylin spent, and 117 is what Rochelle spent. Make sense? That's using matrix multiplication to come up with their totals.